So let's take a look at our new equation and talk about the parts. X equals a cosine square root of k over m times time. X represents where the object is at. So remember, we're talking about a mass that's attached to a spring and oscillating back and forth. So X is what position the object is at. A is the amplitude or the maximum position that the object could be at. K is the spring constant. That's how stiff the spring is. M is mass. That's, how much mass the object has. And T is time. That's how much time it has passed since the object started moving. So let's keep looking at this, and let's look at our more general equation. X equals a cosine omega t. And we want to know how much time, or what's the period for this object. Again, let's think about our mass on a spring. So here's our mass and our spring, and this goes back and forth. And we want to know the period, the time for one complete cycle. Well, we know that cosine repeats every 2 pi. So what happens, what we know is that if we have omega t, when omega t equals 2 pi, then that's the period. That's how long it takes. Or the period is equal to 2 pi over omega. In our previous example, we saw that our omega was equal to the square root of k over m for a mass on a spring. So that means for that case, a period is equal to 2 pi over the square root of k over m, which would result in 2 pi square root of m over k. So that's the period for a mass on a spring. And if you think about it, the more mass that there is, the more time that it would take for this thing to go back and forth. And the more K, the stiffer the spring, the faster it would go back and forth. So more mass, more time, more K, a bigger number in the denominator, less time. So let's take a look at an example here. If we have a mass of 4 kilograms and we hook it up to a spring with a spring constant of 8 newtons per meter, and let's say that I pull this back a distance of 2 meters, and then we let it go, it's going to oscillate back and forth around that equilibrium position. So maybe the first thing we want to know is, what's the period? How long is this going to take for it to go through one full cycle? Well, we know that our equation for x is a cosine omega t, where with a mass on a spring, that's a cosine square root k over m times t. And we know that cosine repeats every 2 pi. So when k over m times t is equal to 2 pi, that's going to be a complete period. So what we have then is, we can say that when 2 pi equals square root of k over m t, or the period is equal to 2 pi over the square root of k over m, which is equal to 2 pi times the square root of m over k. And we have m and k, so the period is 2 pi square root, mass is 4, k is 8. So this results in 2 pi times the square root of 1 over 2. 2 over root 2 is the square root of 2, so this is the square root of 2 times pi. That's how long it'll take for that to oscillate back and forth. The next question, or the next thing we might want to know is, where will this thing be in 14 seconds? So we pull it back, let it go, it's bouncing back and forth. What position, what is the x value as related to the equilibrium will it be after 14 seconds? So we can use our equation again, x equals a cosine omega t, or x equals our amplitude, which we stretched it back 2 meters, cosine omega, and remember for mass on a spring, omega is the square root of k over m, so that's the square root of 8 over 4, and then times time, and we said we want to know when this thing is at 14 seconds. So now we have all these variables in here, and we can calculate what that is. So x is 2 times cosine. It's really 14 times the square root of 2, which is cosine 19.8. So now we need to evaluate this. Are we going to use degrees or radian when we solve for our cosine? Well, remember, we've been saying that this thing repeats every 2 pi. So we're talking about radian values. So make sure you have your calculator in radian. And when I do this, I get x equals 1.16 meters. So what that means is that we've stretched this out 2 meters to let it go. Well, it's bouncing back and forth, and at 14 seconds, it's going to be at this 1.16, so just a little over halfway for what we stretched it out. So it's going to be right here at 1.16 meters. So as a recap here, we have a mass on a spring, simple harmonic motion. It's going to oscillate, repeat that same path, and remember that for simple harmonic motion, we have to have a restoring force that is proportional to the displacement. So F has to be proportional to minus x. So the spring force works nicely for this because it's minus kx. We know that if we look at our x position, it's going to follow some kind of sinusoidal sine or cosine function. And it's going to go back and forth instead of between 1 and -1, amplitude and negative amplitude. So we're going to do the amplitude times that. And it's not going to repeat every 2 pi. So we're going to set up an omega t there to find that out. So our position is going to be x equals cosine omega t. And then remember that we looked at Newton's second law, F equals ma, and we did minus kx equals ma, where we took 2 derivatives of the x function. And through that, we found that omega is the square root of k over m. So that left us with a final equation, x equals a cosine square root of k over m times t.